like I said before, we're just going to kind of roll through as many chapters as we can kind of get to, some of the earlier ones. We're going to kind of hit the highlights of the stuff in there and kind of review it. And again, we'll see where we get to. And then we'll talk about, obviously, the final and when it is, and whatever we don't get to. Like I said, I think I should have some lectures, recorded ones of some of the other reviews for the other chapters, so I'll try to put those up there in addition to, obviously, this one as well. All right, so let's just get started. Again, I'm just kind of going off the top of my head and thinking about what was in those chapters, so I'll refer to our canvas there to see. All right, we're really going to start, actually, I think we did start with chapter 1, but there really was not much going on in chapter 1. It was just about the scientific method. You could probably forget about chapter 1, I'm thinking. So really the main stuff started in chapter 2, if you remember way back then. That was January, I believe, right? And we started with measurements, which hopefully at this point you understand measurements. We talked about units and the two different types of units, kind of the English units, right, and the metric units. And really the sort of combination of metric into the SI units, which is sort of the standardized units used in chemistry. Remember, as we talked about, whenever you take a measurement, you should always look at the scale. And we always want to look at the two sort of important markings on it, the large markings, which are the ones that usually have numbers. So that in this case would be 1 centimeter. We also want to look at the smallest markings and start counting after the last large marking. So if we count that, there's 10 small markings, which means each of the small markings, 1 divided by 10, is 0.1 of a centimeter. And when we do take a measurement, we always record all the certain numbers. So that'd be 1.1, 1.2, 1.3, 1.4. So again, 1.3 would be all of our certain numbers plus the first uncertain number. And that's really, again, where that sort of estimation or uncertainty comes in a measurement. So here again, we may feel it's halfway there. We record 5, and obviously our centimeter unit, that's our first uncertain number. Remember that for the most part, you could usually go to one more place to the right of the smallest marking. You also can find the tolerance of your measurement by taking the smallest marking and dividing it by 2. And that gives you your plus or minus 0.05 centimeters. What that essentially will tell you, right, is how far you can take the reading to. That would mean that in this case, 1.35 centimeters plus or minus 0.05 centimeters is the sort of proper reading here. The reason we do take all the certain numbers plus that first uncertain number is when you do that, that is what we call significant figures, right? And significant figures come from measurements or measured numbers. The other type of number that we come across are exact numbers, which are things that are counted or definitions, and they have unlimited number of significant figures. Now, with significant figures, as a reminder, right, all non-zeros are significant. When we get into zeros, there's 3 types of zeros. There are leading zeros, which are not significant. So again, 0.00123, none of those are significant. We start counting here at the 1. This would have 3 significant figures. There's trap zeros, which are between non-zero numbers. Those guys are significant. And again, 1004, we start counting here, significant all through there. And this guy would have 4 significant figures. Also, obviously, are trailing zeros, which is the one that gives people the hardest time. And that has to do with a decimal place or point. And if there is a decimal point, then it would be significant. If there is no decimal point, then all the zeros at the end are not significant. So again, if you wrote something like 600, this 6 is the only significant figure there. If you wrote something like 600 and did put the decimal point, those zeros at the end would become significant, and we would have 3 significant figures. Now, another important thing is significant figures and calculations. And when we do calculations, We do look at one of two sort of things usually. We either multiply or divide, and when we multiply or divide, it's the number of sig figs we're looking at, and the answer should match the lowest number of sig figs in your calculation. So whichever one has the smallest number of significant figures in your calculation is how many your answer should have. And obviously as well, if we add and subtract, which is our other sort of deal, we are actually looking at decimal places here. And it's also the smallest, and your answer should have the same number of decimal places as the one with the smallest. Remember, that's not always the same as the number of significant figures. So if you're doing some combination thereof of a problem, we would do this part first. This has 2 sig figs. I'm sorry, that has 3 sig figs. This guy has 2 sig figs. And that means the answer on top should technically have 2 sig figs. We then would be dividing by 2 sig figs by 4 sig figs, which means our answer should end up with 2 significant figures when it's at the end. Also a reminder, right, as you're doing calculations, you should avoid really rounding too much right until the end. Keep a couple of guard digits and all that good stuff so that you don't get sort of rounding errors. Any questions on that there? In relationship to this, right, we talked about scientific notation. And again, proper scientific notation has this format. That again is a number between 1 and 10. It is not 1, it's not 10, but does need to be between them. And this is either positive or negative depending on which way you need to move it. So obviously if I had 123, 2 places, 1.23 times 10 to the 2. Positive if it's a large number, 0.001. 2, 3 places, 1.00 times 10 to the minus 3. Negative exponent if it's small. When you do write a number scientific notation, remember this front number is always significant. So we should never lose any significant figures as you go from scientific notation to decimal and back. Probably more important when we talk about scientific notation is your calculator and making sure again that you use your exponent buttons, whichever buttons your calculator's got. And we talked about some differences here. Reminder, this guy usually parentheses around everybody, right? These guys, you don't have to do too much parentheses and stuff like that. So remember, always use your exponent button when you're doing scientific notation, and also always use your negative button, not your subtract button, if you need to make something that's negative. So that's some of the stuff that we talked about. We also talked about some kind of conversions, and we talked about some prefixes that we sometimes use with metric numbers to change the meaning. So for example, nano is 10 to the minus 9. Centi, right, is 10 to the minus 2. And a reminder that when you're using these, you do want to do it kind of correctly. So when you see that, that is how much there is in the base unit to one of the prefix units. So for example, if I had meters and nanometers in one of the prefix units, which would be this guy, this is how much there is in the base unit. So that again is the proper way to do that. Again, it doesn't matter really what the unit is. It could be liters and nanoliters. 1 nanoliter would be 10 to the minus 9 liters. By the way, 10 to the minus 9, 10 to the minus 2, or any of those versions of that basically is 1 times 10 to the minus 9. If you need to punch it into your calculator, again, you'd punch it in scientific notation. Remember that we could use these as this is what is known as an equality. And an equality does give you 2 conversion factors, which would give you 10 to the minus 9 meters over 1 nanometer. Our 1 nanometer is 10 to the minus 9 meters. Also something really important we talked about in this chapter is how to set up your problems and do your work, which is dimensional analysis. Remember, dimensional analysis uses conversion factors and opposites cancel. So if we had something like 590 nanometers and we wanted to know how many meters that was, we could think of it as a fraction. And again, nanometers are on top, so we want them in the opposite location. So we could go 1 nanometer would be 10 to the minus 9 meters. When we do dimensional analysis like this, we always multiply whatever's on top and we always divide what's on the bottom. As we talked about throughout the semester, sometimes it's better to take a dimensional analysis approach because you don't have to worry about rearranging the equation correctly. It will kind of do it for you. And as long as you remember, multiply on top, divide on the bottom, you'll be in good shape. So obviously here, in this case, we will end up with basically 590 times 1 times 10 to the minus 9, and that's going to give us our number here of 5.9 times 10 to the minus 7. And these would be meters as these units would cancel. When we do calculations like this, especially in dimensional analysis, for the most part, our conversion factors here are going to be considered exact numbers, which this one would be. And that means that we would default back to our original number here, which has 2 significant figures. And again, that is why we ended up with 2 significant figures here in our answer. Remember that when we look at conversion factors and trying to determine if it is exact numbers or not, if you are doing anything that's an English to English conversion, that's considered an exact number. If you do any type of metric to metric conversion, that also is an exact number. And if you cross over, though, from English to metric or backwards, those are really the ones that you do need to look at. So we'll put a little happy face there to look at it. These are exact numbers here. And basically, you will always have in that sort of conversion, usually the conversion factor where there's a 1 of something equals an actual number. It's the actual number, obviously, that you would look at, not the 1 in terms of significant figures. There are a few exceptions. 1 inch, right, is exactly 2.54 centimeters, so that's an exact conversion. They also wanted you here to learn 1 pound, I think, is 453.6 grams. They consider that an exact conversion here, even though really it's not, but we'll go with it. So those are exact numbers or conversions, pretty much anything like that. Like if you want to know how many quarts in a milliliter, 946 or whatever it may be. So you would use that number for your sort of significant figures. So the only time you really have to worry about if you're doing some type of scientific calculation and a conversion is that English to metric conversion. But other than that, if it's not, it's considered really an exact number. Probably 9 times out of 10, as you probably have seen, you're going to probably end up with kind of like the same sig figs as the original number. That usually is a fairly good sort of location of where it needs to be. Now, the last sort of thing I think we talked about in this chapter was density. And density is a formula of D is equal to M over V. Common units of density are grams per milliliter, or grams per cubic centimeter. Remember that 1 milliliter is equal to 1 cubic centimeter. And we can rearrange the density equation. Volume is equal to mass divided by density. Our mass is equal to volume times density. Again, you could do like your DMV triangle if you like. And again, density is mass over volume. Volume is mass over density. And mass is volume times density. Now, in terms of the volume part, there's a few different ways that we can get the volume in these type of situations. Obviously, here we could just simply, like you've done in some labs, read the meniscus and just take a reading of the milliliters. We also can, if it is a solid, like that square cube you had, you could take 3 length measurements, the length times the width times the height, and measure each of them in centimeters. And that gives you a cubic centimeter, which is a volume. So remember, when you take sort of a length measurement in cubit, decimeters cubed, centimeters cubed, you're talking about a volume. If you're talking about just centimeters by itself, it is not a volume, it's a length. And probably the most common way in density that we sort of get the volume of an object is volume by displacement. So we fill up a certain liquid, we take some type of solid, dump it in. What happens is the liquid in there will rise to a final level, and we can find the volume by taking the difference in the two volume readings. So the volume of the object will equal our final volume minus our initial volume. So there's again three common ways we get to sort of the volume with density. Also a reminder that if you did have the density of a substance, like something was 1.2 grams per milliliter, you can use that as a conversion factor. And you can use it with grams on top, milliliters on the bottom, milliliters on top, grams on the bottom. And you can then take a more dimensional analysis approach, and you won't have to worry about rearranging this equation correctly, because it should really do it for you as long as you go opposites cancel and get rid of the units that you want. Any questions on any of that there? All right, I believe that was chapter 2. Then after chapter 2, we rolled into chapter 3. And chapter 3 was about matter. It was a very short chapter, if I remember correctly. And obviously, we talked about the different states of matter in this chapter. So we had solid. Again, everybody packed in relatively close to each other. Not a lot of energy, not a lot of movement. We also had liquid, where they are still packed in relatively close to one another, a little bit more room for movement. They have a little bit more energy, which is why they can move around each other and why liquids are fluid. And then obviously we have our gas state, where things are completely broken apart from another and flying around. We also talked about, I think in this chapter, the transitions that occur between these as we go from solid to liquid. That's the process of melting. As we go from liquid back to solid, that is freezing. Liquid to gas, that is evaporation or vaporization. Gas back to liquid is condensation. We could go directly from solid, skipping the liquid cleanup, and go directly to gas. That is sublimation. We could also go backwards, gas, skipping the liquid back to solid. That is deposition. Remember that these phase transitions actually occur at the same temperature. So for example, here, melting and freezing would occur at the same temperature. If we're talking about water, we're talking about 0 degrees Celsius, the normal melting point, freezing point of water. Evaporation and condensation also occurs at the same temperature. For water, that is 100 degrees Celsius, the normal boiling point in this case. It just depends at those sort of temperatures, what you do as to which way you would go in terms of energy. But exactly at 0 degrees Celsius, you do have both phases in equilibrium with each other. So you have some liquid water and you have some ice, like ice crystals happening. And the same thing at sort of 100 degrees Celsius, you got some steam happening. And you also have some liquid water basically happening. As we go from solid to liquid to gas, those are all endothermic processes. Energy is absorbed. And obviously, as we go the opposite way, if we go from gas to liquid to solid, energy has to be released for everybody to slow down. And that is an exothermic process. Energy is released in this case. Questions on that there? All right, then we talked about a few things, I think, as well. We talked about elements, right? Talked about molecules, and we talked about compounds. And a reminder that elements are your basic units of everything. And most elements come as monoatomic, which means they come as one atom. There are certain elements that come as diatomic, which means they come as twos, like hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine, and iodide. So these guys all come naturally as twos. A definition of a molecule is two or more atoms together. And remember that a molecule definition means that it's just that basic thing of two or more atoms. They could be the same element or different elements, and they could be molecules. But when we talk about compounds, it's two or more atoms of different elements. So when we have something like water, that is a molecule because basically, right, it's got definitely more than two atoms or one atom. And in this case, it's also a compound because it contains atoms of hydrogen and oxygen. It is not an element, obviously, because it contains two different elements involved. If you take any of these guys, like oxygen, that is an element because it only contains oxygen. It is also a molecule because it meets the basic definition of two or more atoms together. It is not a compound because there's only one type of element involved in the thing. Questions on that there? This is also where we got into the idea of pure substances. And pure substances is when you have just obviously one thing. So water is an example of a pure substance, sodium chloride, iron, whatever it may be. These are all pure substances. When you take two or more pure substances and put them together, you get a mixture. Where these substances do retain their identity, and we talked about two types of mixtures. We have a homogeneous mixture. Everything looks the same throughout. Everything will mix really well. So for example, if you took your sodium chloride and your water, which are two pure substances, and you put them together, you get a sodium chloride solution, which just looks like water, but obviously has some salt in it. And that would be an example, obviously, of a homogeneous mixture. In a heterogeneous mixture, we see different layers, are phases. And so, for example, if you took water, which is a pure substance, and you added sand, which is also a pure substance, you basically will get some sandy water, right? And you can mix that mixture as much as you want. The sand will never dissolve in the water. You will always see it. And that is an example, obviously, of a heterogeneous mixture. Also, something else that we talked about in this chapter was the idea of physical changes and chemical changes. And when you make a mixture, it is a physical change. Physical properties are things like boiling points, melting points, and things like that. And when you have a physical change that occurs, what you start with and what you end with are the same, basically. They are fundamentally the same thing. They may just look different, but they are essentially the same. So obviously, if you took water and as an ice cube and you took it to water in the liquid state, they are both H2O. It didn't fundamentally change to anything new. You didn't create anything new, but it just looks different. It's in a different phase. And changes of phase are very common physical changes that occur. That's different than in a chemical change. What you start with and what you end with are different. You made something new. So, if you took some iron and you took some oxygen, they could come together to make iron 3 oxide. I did that backwards there. Do that. There you go. A little iron 3 oxide, and that's rust. And obviously, this is something fundamentally new that was made versus these things. The key with the chemical change, which is usually a chemical reaction, is you cannot get back the original components by any type of physical means, which means you can't separate them, you can't freeze them, boil them, whatever you want to do. You can't get back to original substances without a chemical change occurring. Also, the formation of water, right, is an example of that. Balance it like we're in chemistry class here. That's a chemical change. There's no way you can do whatever you want with the water. You'll never get the hydrogen gas back or oxygen gas unless you do some type of chemical change, a reaction like running electrical current over it and do some electrolysis of it. And that is a chemical change that will happen that will convert it back into its elements. And you can take a compound back to its elements. But once you hit the elements, that is as far back as you could go. You can't go back any farther than that. Now, because mixtures are basically a physical change, the substances retain their identity. We talked about a couple of ways you could separate them out. If you have a solid and a liquid, filtration is probably your best bet there. A little filter paper action, right? So when you take that and you pour it, all of the solids can get trapped on the filter paper because it gets too big to go through. All the liquid will be able to travel through. And again, just by this physical process of filtration, you could get back, for example, if this was your sand and water, you could get the sand back over here and you would have the water dripping out over here. You could also do that, was an example there, obviously, of a heterogeneous mixture. You could do something like our sodium chloride example or our salt water. And that's a homogeneous mixture. And a fancy way of doing it is you could set up a really badly drawn distillation apparatus here with some salt water. And a reminder that it's kind of connected with a closed system of a cold tube. You heat up the water here, water is going to start to evaporate and go into the gas phase. As the gas phase hits the cold, it's going to go through condensation and it will drip out on the other side. And if you continuously do that, eventually all the water is going to evaporate. You'll be left with some red salt on that side over there. And now again, through this process here of physical process, you actually separated out both of the components of this mixture. You're actually using physical properties to separate it out because water only needs to get to 100 degrees Celsius to go into the gas phase. Salt or an ionic compound needs a much, much, much higher temperature. You could heat the heck out of a salt and it will never go into the gas phase. So by using that difference in physical properties, you're able to separate out these mixtures. Any questions on that there? All right, that is chapter 3. Then we skipped ahead and jammed into chapter 10, I think. And chapter 10 is about energy. And in chapter 10, common units of energy that we talked about are joules are kilojoules. Also, calories, lowercase, are kilocalories. The relationship between joules and calories, there is 4.184 joules is equal to 1 calorie. That's also the specific heat capacity of liquid water, which is why that conversion is like that. We talked about a couple of different things, obviously, in this chapter. We started with, again, a little bit more of a talk of our exothermic reactions versus our endothermic reactions. And we talked about some energy diagrams and what they look like. And a reminder that if this is energy here, in an exothermic process, we have something that looks like this. This is our reactants, this is our products. And again, on an endothermic, looks maybe something like this. Reactants to products over here. So this is the energy as the reaction progresses in this direction here. This is the energy diagram, and remember that when we have a chemical reaction, the only thing that changes is bonds. So we make and break bonds, which is all electrons. That's also why we have conservation of elements, because we don't do anything in the nucleus. It's only electrons. And remember, it's the protons that determine whether or not we kind of change elements, and we don't do that in chemical reactions, just making and breaking bonds. So as these reactants are heading up this hill of energy, they're starting to break some bonds and actually start making some bonds. till they get to the very top here, and this is what is sometimes referred to as the transition state. It is the highest point in energy in this reaction. And at the very top, we usually have something there that is referred to as the transition state complex. And remember, that is really a lot of times a substance that has those partially broken bonds and partially made bonds, which is why it's the highest point in that reaction. It doesn't usually hang around a very long time because, as we know in chemistry, things do not like to be high energy. Really, the purpose of everything we do is to try to get things to a lower state of energy. So it usually will drop down a little bit faster. Now, when we look at the relationship here between the reactants and the products, the reactants are higher in energy than the products, and that's how you know it's an exothermic reaction, because in order for the reactants to get down there in terms of energy, energy has to be given off in this case, or released. There is that hill that they climb, and that hill right here is what is known as the activation energy, the E of A, and that is the minimum amount of energy needed for a reaction to take place. It is, again, that hill that the reactants has to climb to get to the other side. Here on this side, this would be our activation energy that we need to do in this particular case. And again, that would be our transition state. If we take the difference between where the reactants are in energy and where the products end up in terms of energy, that is another thing we talked about in this chapter, which is the change in enthalpy, or the delta H of the reaction. Remember, to calculate the delta H of a reaction, you take the delta H of our products minus the delta H of our reactants. If you remember, you go to the table, look up all the values, multiply by the values in the table, and multiply them by their coefficients. And basically, in this case, if we look what's happening, our products are actually lower in energy, so that's a smaller number, minus our initial reactants, which are higher in energy, which is a larger number. So if you take a smaller number minus a larger number, you will end up with a delta H that is negative. And a delta H that is negative means that the reaction is exothermic. So we do expect this to be a negative value here. If you look at this one here, this is our delta H here, the difference between the energy of our reactants and our products. And again, if you kind of do the same calculation for an endothermic reaction, in this particular case, our reactants are lower in energy than our products. So you'll have a larger number minus a smaller number, and that will yield you a positive number here. So if you are given the delta H for a reaction, you could look at the sign, and if it's negative, it means it's exothermic. If it's positive, it's endothermic. And that holds true for most energy values. If you calculate an energy value and you do end up with a negative number, that usually indicates that process is exothermic, and endothermic if it is positive. That's why it's important when you do calculate energy, you don't disregard the actual sign of it. So if you do get a negative number, it is actually important to kind of let you know that. One way that you can speed up a chemical reaction is to add a catalyst. And a catalyst, again, is not a reactant, not a product. It is there really just simply to more efficiently allow that reaction to occur. Because it finds a more efficient pathway for that reaction to occur, it ultimately will lower this activation energy. So in a catalyzed reaction, it will be able to lower this activation energy. The result of that is, because the hill that they have to get to the other side is smaller, you usually will have a lot more reactants that can get up and over or have enough energy to do that. And that usually results in the rate of the reaction increasing because of that, because you have a greater proportion to do that. Again, it's like if you had to walk a giant hill to get to the other side. Not a lot of people would want to do that, but if it's the kind of a really small hill, a lot more people would be happy to kind of go up and over to the other side. It's not going to take that much. Any questions on that there? So as I mentioned with this, we also obviously talked about change in enthalpy. And again, you can calculate that by taking the delta H of the products minus the delta H of the reactants. And so, for example, if you did have an equation like this and you went to a table to find these values for A, B, and C, and it is, minus 100 kilojoules, 20 kilojoules, and minus 36 kilojoules. To calculate this, we would take the delta H is equal to 3 because of the coefficient times the value we would find in the table. That's all of our products. We then would subtract it from our reactants. There's 2 times the value you would find in the table plus our other reactant. Coefficient is 1 times that guy. And basically add that all together and kind of subtract them. And in this made up example here, we'll see how I did. We'll see minus 36 minus 2 times minus 100 plus 20, I think. Gets us something like 72 kilojoules in this case. This would be an endothermic reaction as we have a positive value for delta H. Any questions on that there? We then also in this chapter talked about specific heat and specific heat capacity, sort of another energy sort of value. And we talked about specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. For example, the specific heat of liquid water is 4.184 joules per gram per degree Celsius. That's what those units stand for. Amount of energy needed to raise 1 gram of a substance by 1 degree Celsius is basically the definition. There is an equation that goes with that. Q is equal to ms delta T. That is energy or heat. And that has units of joules or calories usually. M is mass, which has units of grams. S is our specific heat capacity, which has either joules per gram per degree Celsius or calories per gram per degree Celsius. That is the guy that has all 3 units, oftentimes confused with Q. Delta T is our change in temperature, and that is our final temperature minus our initial temperature. As one of the few things in chemistry that we actually do usually leave in degrees Celsius. You don't have to convert it to Kelvin, and that's because your specific heat capacity is usually always in degrees Celsius. When you calculate Q, if Q is a positive number, that's an endothermic process. And again, if you calculate Q and it's a negative number, that is a exothermic process is going on. It is also important here to do the change in temperature correctly. You always want to do final minus initial because this number is positive. Specific heat capacity is positive. So really the only way Q can be a negative number is if you do the temperature change correctly. So if you always do large minus small, you'll never get a negative, right? Because you always did have large minus small. So you do want to make sure again with energy that if it is negative, you keep it there. And you can do that by doing final minus initial. We see our temperatures increase when a substance is in an endothermic process because they're absorbing energy. Their temperature will rise, so their final temperature is higher than their initial. When somebody is exothermic and loses energy, we see their temperature actually start to decrease, right? Because they're giving off that energy. So their initial temperature is actually higher than their final temperature. And that's where we get the negative value in the change in temperature and also the negative value in our Q. We also talked about the transfer of energy here. So much like you did in lab as well, you can have some water. You could have like a piece of metal, for example. And if this metal was at like 98.5 degrees and your water is at 25 degrees and you dump this metal into here, in terms of the metal, because it is hotter, heat transfers from hot to cold. It's going to release all that energy into the water. The result of that is we will see the water's final temperature, for example, increase. We'll call it 27.5 degrees Celsius. But what will happen to the metal is because it's sitting in that water, the final temperature of the metal will also be the same. as the water, 27.5 degrees. So again, because the metal is releasing the energy, its temperature goes down. Because the water is gaining the energy, its temperature actually goes up. There's a relationship when you do something like that, that Q of the metal is equal to negative Q of the water. And that means that if the water is endothermic and picking up the energy, it will be a positive value for Q, and a negative will mean that our Q for our metal should be an exothermic or negative value. If the water is actually releasing the energy, then it would be negative for our water, and negative would turn our Q into a positive number, and that would mean actually the metal's picking up the energy. So if you did the opposite, for example, of what we commonly do, which is instead of heating the metal, but take the metal out of the freezer. The metal is now colder than the water temperature. So when you put it into the water is actually going to send its energy into the metal, and it's going to actually warm up the metal in that particular example. And it would be exothermic for the water and endothermic for the metal. So it always flows again from that heat energy. So the sign is really important here, in that relationship with the negative allows you to change it. Any questions on that there? We talked about also, I think, briefly equations and what you could do with equations and the energy that's associated with it. So if we had an equation like this where the delta H value was 100 kilojoules, and if for some reason we needed to reverse this reaction, we can do that. And what happens to delta H is the sign will change. So instead of positive 100, it would be negative 100. If we needed to, for example, multiply this entire equation by 2, that would give us 2a plus 2b goes to 2c plus 2d. What happens to the delta H is we would take 2 times 100 kilojoules, and that would give us 200 kilojoules in this case. Or if we needed to divide by 2, if we divided by 2 this equation, we would actually get back to that equation, and we would divide the delta H by 2. So the delta H here would go 200 kilojoules divided by 2, which would take us back there as well. So if you need to multiply an equation by a common number, then you multiply the delta H. If you need to divide an equation by a common number, you divide the delta H. If you need to reverse the reaction, you would reverse the sign of delta H. Why you might need to do that, again, the idea of Hess's law, which is not all reactions occur in one step. You could do it in multiple steps. So for example, if I was looking at this equation here, and delta H here was 10, and the delta H here was 20 kilojoules. If I wanted to figure out the delta H of this reaction, I basically just need to kind of rearrange these equations correctly. So since A and B are on the left, it is over here. I don't actually have to do anything with that top equation. I could just leave it the way it is, which means my delta H would be 10. The bottom equation, I actually need to reverse it. And that would mean if I reversed it, C plus D gives me E plus F. And because I reversed it, it's now negative 20 kilojoules. Let's change the sign. If I add these together, anybody on opposite sides of the arrow that are the same will cancel. It's like subtracting to the other side. And then everybody on the left-hand side of the arrow stays there. Everybody on the right-hand side of the arrow stays there. And now I have built this reaction from the other two. And to get the delta H of this one, I basically just add those numbers together I did, which would be 10 plus negative 20, going to give me a negative 10 kilojoules. And overall, this reaction would be exothermic because it's a negative value for delta H. Question on that there. The last thing we talked about is actually, for example, you can take an equation like this and you could kind of do some stoichiometry with it using as a conversion factor of moles to energy. So for example, in that top equation, I could say for every 1 mole of A, I get 100 kilojoules of energy, and I could use that as like a conversion factor. A mole of A gives me 100 kilojoules, or 100 kilojoules gives me 1 mole of A. So again, I can use it as a conversion factor to go from moles to energy. And you can do that. Obviously here, that would be 2 moles of A would give me 200 kilojoules of energy. You can do that for anybody's here. 2 moles of C would also give me 200 kilojoules of energy and so forth. So you can kind of do like a stoichiometry between moles and energy. Any questions on that there? That is chapter 10 in exam 1 materials. So after that, we went backwards to chapter 4. And in chapter 4, we started to talk about atoms in this chapter. Remember, atoms were made up of protons, electrons, and neutrons. And there was a number of experiments that we talked about, right, that helped us understand that. Some of the highlights of those experiments, we had the cathode ray tube that Thomson used to explore electrons, along with Milligan, who did an oil drop experiment to also sort of explore electrons. And basically, we had the charge to mass of an electron there from Thomson. We had the charge of an electron found by Milligan. So we had kind of this deal, charge to mass or mass to charge, and the charge of an electron. And by using both of those things, the mass of an electron was discovered. That led to sort of a early model of the atom that was done by Thomson, and that was our plum pudding model of the atom, where we had basically a sphere of positive charge with electrons embedded inside. And it was believed at that point that it was the electrons that made up most of the mass of the atom. And this was sort of the accepted model of the atom until really the next major experiment that came along, and that was Rutherford and the gold foil experiment. And remember, Rutherford basically shot these alpha particles, which are positively charged particles. I know the party's next door. At these things. And what he expected to happen was, because he shot these positive alpha particles, he expected them to go through with some deflection because it's positive on positive. Similar charges repel each other, opposite charges attract each other. What he saw, as we talked about, was pretty much most of them sailed through with no problem. And every now and then we would see an alpha particle scattered at a really large angle. What that meant was he had to kind of abandon the plum pudding model and come up with the new model of the atom, which was the atom is mostly empty space. It has a dense positive core, which is our nucleus. I'll go over here. And later experiments found that protons are in the nucleus, which are positively charged, and neutrons as well, which have no charge in the nucleus. And the other major difference was most of the mass of the atom was actually the nucleus. And that made a lot of sense because later experiments showed that both the proton and the neutron were about 1,800 times heavier than any electron that was present. And actually, out of all three of those particles, it's the neutron that is the heaviest. It just barely beats out the proton, followed by the electron, which is obviously much, much smaller. Now, we also talked about before that, right, Dalton, and the important thing there, right, is obviously he went bowling on Thursday. That seems like a good one there. So that's important there. Along with that, like, atomic theory thing he had going on for himself. Any questions on that there? Then in this chapter, we got into some other aspects of the atom. Mainly, we talked about atomic number. The atomic number is sometimes abbreviated with a Z. That is the number of protons there are. And remember that the atomic number is found on the periodic table It is that number typically above the symbol. Because if an atom is neutral and it contains protons, electrons, and neutrons, if you know the atomic number, the number of protons, and it is neutral, it will also tell you the number of electrons it has. But again, the definition of atomic number is just the protons. We talked about mass number. Mass number is the number of protons plus the number of neutrons. And those are important because you can take the mass number and subtract the atomic number, and that will get you your number of neutrons. Remember that when you calculate or give the mass number, the atomic number, the number of protons, electrons, and neutrons, they all should be positive whole numbers. And that is why when you go to the periodic table and you look at the number on the bottom, that is not the mass number. That is the atomic mass, which is different. And again, none of those guys on the bottom are pretty much whole numbers, so that's a good way to remember it. We also talked about isotopes, and isotopes are basically the same element, but different mass. And because protons are the things that make something a particular element, it is actually the number of neutrons that change here. And we could write that symbol a certain way where the mass number is top left, atomic number is bottom left there. And so, for example, if we took copper 64 and 29, again from the periodic table, copper 29 there, we will have our number of protons. Because this is neutral, there's nothing written there. We would have an equal number of electrons. So again, we would have 29 protons and 29 electrons. Positive, negative gives you 0. And our number of neutrons in this case would be our top number, mass number, minus our atomic number, giving us 35 in this case for our number of neutrons. Remember that if you do have something with a charge, you do have to take that into account. So if we have the same guy, but with a +2 charge, we would still have 29 protons because of the atomic number. But in this case, we actually would only have 27 electrons. 29 positive things and 27 negative things leaves you a +2 left over, which again is where the charge comes from in this case. And obviously our number of neutrons here would be the same. 64 minus 29 would get us our 35 neutrons in this case. So when something gains a charge, which obviously is an ion, the only thing that changes is the number of electrons, right? Questions on that there? In this chapter as well, I believe we hit the periodic table. And again, hopefully you're familiar with it, but when we draw the generic box of a periodic table, right? And we have groups which go up and down, and we use the representative numbering 1, 2, 3, 4, 5, 6, 7, and 8. We also have periods which go this way, right? So groups go up and down, periods go left and right. There are 7 periods on the periodic table. Some of these groups have special names. Group 1 is our alkali metals. Group 2 is our alkaline earth metals. Group 7 is our halogens. Group 8 is our noble gases, right? We also have kind of like a staircase thing happening right around there. In the middle of 2 and 3 are transition metals, which obviously, as you know, have variable types of positive charges. To the left of our staircase there, these are metals, also the 2 rows on the bottom, which actually go right about there on the periodic table. That's our lanthanide and actinide series, which are also metals. Upper right of the staircase is our nonmetals. And the staircase there coming down is our metalloids, are semi-metals, right? Which are guys that have basically characteristics that are similar to metals and non-metals. Characteristics of metals, right? Good conductors of heat and electricity, shiny. Non-metals, bad conductors of heat and electricity. They're dull, they're brittle. And like I said, metalloids have kind of properties that fall on both sides of that sort of spectrum. Any questions on that there? We also, I think, did officially talk about ions as well in this chapter. So again, ions are things that have a charge. They could either be positively charged, which are cations, and that happens because we lose electrons. That is typically, as we talked about, metals that do that, right? We also have anions, which are negatively charged. These are typically guys that gain electrons, and those are our nonmetals that typically happen. And as we talked about there a second ago, it is the number of electrons that change. So like we saw in that copper example, we actually have two less electrons. And that's what the positive charge means. You've lost electrons. The numbers, how many electrons you lost from the neutral atom. If we had fluorine, fluorine has 9 protons and 9 electrons in its neutral state here, gives us 0. Fluorine will make a -1 charge, and it has 9 protons because it's got to stay fluorine. In this case, it'll actually have 10 electrons, one more, and that leaves us a -1 charge that's left over in this case. Now, since we do have the periodic table up here on the previous slide, reminder that things on the periodic table do not have charges unless they start hooking up with each other, like metals and nonmetals. But when they do gain charges, there are things that have sort of fixed charges. Things in group 1 are +1, things in group 2 are +2, things in group 3 are +3, which is usually aluminum, is most of the time that we're talking about there. We do skip 4, and then non-metal region here, we do go -3 on group 5, -2 on group 6, and -1 on group 7. A reminder again that transition metals do have a variable type of positive charge. There are 3 exceptions. Zinc and cadmium both have a +2 charge. Hanging left there at cadmium to silver has a +1 charge. So those are kind of like that backwards L there is the 3 sort of exceptions in the transition metal region in terms of their charge. Any questions on that there? Now, with talking about ions, I believe we also finished up that chapter talking about electrolytes. And electrolytes are substances that break apart into ions in solution. And it's really that presence of the ions that help it conduct electricity. So it's able to conduct electricity. We talked about strong electrolytes, and they 100% break apart into ions. So something like sodium chloride, if you had a solution of sodium chloride in that actual beaker, for example, it would completely break apart into sodium ions and chloride ions 100%. You would have none of these units still together in a beaker of it. Basically just those ions floating around. And because you created a lot of ions in that solution, it's going to be able to conduct electricity really well. So it's going to be a very good conductor of electricity. I think we maybe use the light bulb example. And if you had a light bulb, it would be very bright. It would go on and really shine very brightly because it's going to conduct electricity really well. That's different than a weak electrolyte. In a weak electrolyte, it will mainly stay together, but break apart a little into ions. So if you had something like HF, which is a weak acid, and a lot of weak acids, weak bases, or weak electrolytes, it will have those arrows heading in both directions, as we talked about in chapter 17. It will actually set up an equilibrium between that and H plus and F minus. The difference is you will mainly have this guy in your beaker, but you will have a few of these guys produced. So if you were looking at that, you mainly have the HF unit still together, but a little bit of ions are actually formed in this case. Since it's able to still produce a few ions, it's able to conduct electricity, but it would be very dim, say the light bulb example, it would turn on, but it looks like it's dying and not a lot of electricity sort of happening. This again is that reversible reactions we talked about in chapter 17 in more detail. Again, it has a forward direction and a reverse direction. And again, it will reach equilibrium when those rates are the same. Remember, a strong electrolyte you can think of as like a one-way street. Everybody's dumping out on the product side. A weak electrolyte is going to go back and forth in a kind of a two-way street type situation. Lastly, there's a non-electrolyte, and a non-electrolyte will dissolve in, say, water, but no ions are formed. And because of that, it will not conduct electricity. So, for example, sugar, if you were to dissolve sugar in some water, you would be able to dissolve that sugar for other reasons. But because sugar is made up of carbons, hydrogen, and oxygen, there's no ions. This is all covalently bonded together. And because there's no ions, it will not conduct electricity. Any questions on that there? Okay. So I think we'll lay it up there and we'll talk about